That roof is on fire. Oh, we gonna take
It's definitely about to be exciting. I feel like this math is more exciting than the first one, because now you are really doing calculus. Because the first one it had other things and calculus. Calculus was only done towards the end. So now you get to do calculus. And I think guys, calculus is fun and just it just needs practice and dedication. You cannot pass without enough practice. Whatever you'll be doing in this module needs practice for you to master it. Excuse- So, what teaching what teaching method do I use? Um, like I said, guys, I'm gonna start at 10 past. Hence, people are still coming to avoid stopping, and admitting people. So, the first thing that we're gonna do today is techniques of integration. So, I'm gonna do the first three critical techniques. Then after we're gonna do in the next session we're gonna do others as we go. But now what I'm gonna encourage you to do when after every session, when you got something from the sessions, go home, practice, practice, practice. What I do usually I send recommended problems for you to do when you're alone at home. That's very important. Trust me, if you pay attention in class, because I'm gonna be doing problems. That's how math is taught, by doing problems. I explain something, what is it, and I do a problem. That's how you're gonna see. That's how you're gonna see how the problem is solved. That's the only way. Then when you're alone now, when you got all the concepts, all the important concepts, you sit down when you're alone, and now you start practicing, 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 and the practicing. Okay, so now I'm gonna start in 3 minutes. Well done, guys. You passed engineering maths 1A. We usually lose soldiers there, but you haven't lost you. You're still here. So you should applaud yourself. You did something. You understand? Yeah, you're already an engineer now. You're going there. Baby steps, but yeah, you're going there. So now I'm gonna wait for 2 more minutes. It's not easy, guys. Some people, some soldiers, we lost them. We lost our brothers and sisters. Same as 1B. Now, 1B, we lose more brothers and sisters. 1B, we lose more brothers and sisters, by the way. So you can see Oriane. It's not getting easy. We still lose brothers and sisters in 1B and more. So if we lost 20%, 1B we lose maybe 40%. You understand? So yeah, it's tough. Which is why sometimes I'll be guiding you. Oh, by the way, guys, if you're going to be doing ETN Electrotechnics 1B, I'll be helping you guys for free. Nice, ne? Nice. I'll be helping you guys for free with ETN. Just giving you the tricks on how to solve the circuits, both outcome A and outcome B, so you can get your 100% and leave. Because ETN has an open book test, but it's a scam. Go there when I'm thinking it's an open book, you'll fail dismally. On. So that's why I'll be teaching you all those methods. You just walk in there, take your 100 and leave. Okay, I'm gonna start in a minute now. I think everybody wanted to join the class. So yeah. Hey, pra gift.
Hey, good morning, guys. Good morning.
Morning.
Hey, morning.
Mara pra gift don't disappoint.
Evening. Hey, you see, academic stress, man. Yeah, no, apologies for that. Apologies. So, yeah, guys, I just wanted to say that those of you who joined now, because I just sent the link now, apologies for that, ne? It was my delay. I forgot to send the link earlier. So, yeah, also to Mr. Sana, just forgive me. Just forgive me. Yeah, next time I'm gonna send the link earlier. That's just what I wanted to say, guys. Yeah, askis. Ke kopa tshwarelo. Uxolo. Like a yammer. All right.
Ah, ah,
Ne.
ah.
Sharp, sharp.
We don't forgive that. Sharp, sharp. Okay, guys. So we're gonna do the first thing that you're supposed to do. Which are the techniques of inter? Okay, let me admit someone. Oh, am I recording the session? Yes, I am. Okay, I'm gonna do the first thing, like I said, which is your techniques of integration. So now, in Materna or Engineering Maths 1A, you were introduced, like I said, towards the end, you are now doing calculus, your derivatives, your limits and continuity. Now you did chapter 5, which are your antiderivatives. So now, when you were doing antiderivatives, it was easier. For example, you were asked to integrate maybe cos x dx. So the moment you see dx, you have to integrate in terms of x. It was not a problem. The answer was just positive sine x. Then you need to add c, a constant, which is not a problem. This was an indefinite integral. Then you did a definite integral, which had boundaries. Maybe they say from 0 to pi. Same thing, cos x dx is equals to. So now this becomes sine x. No plus c, but you need to evaluate this integral at the boundary. So now you need to start here at the upper boundary to the lower boundary, meaning you have to say sine, then you substitute the pi minus sine, then now you substitute the 0, then you get your answer. Ne? Okay, let me admit someone, which was not a problem. So now remember, when you're finding integral, we are saying it's the reverse of derivatives, which is true. For example, derivatives, what did you learn? You learned your product rule, right? Product rule. Then you learned your chain rule. These were for deriving. These were derivatives. Ne? So you remember, when do we use the product rule when you derive? When you have a product of two
Yes,
functions.
we don't see your
Yes.
screen. You're already cooking, but we don't see your screen.
Mara, please, you can have it. Awa, Mara, wana, awa. Awa. Hey, because guys, I had another class now. Ne? I was presenting. So I'm thinking it's still presenting. Wana, so many people are quite it's fine. So like I was saying here, I hope now you can see. So now when you are deriving, let me admit this person. So when you are deriving, you were deriving when you had the product of two functions, meaning the first function might be f at x multiplied by the second function being g at x. So remember, when you were deriving this, you were using a product rule, meaning you derive the first function, you multiply by the second one as it is, plus, then now you derive the second one, then you multiply by the first one as it is. So we're using the chain rule. Hey, sorry guys, I'm admitting people. So when I'm on wait, I need to go out and admit the person. Okay, so the chain rule, you were dealing with it when you had composite functions. Konje, what are composite functions, guys? When you have a function inside another function. Okay, no problem, because we are not deriving. Now, the techniques of integration is simply the reverse of these rules you did when you were deriving. Okay, how? The product rule has its own reverse technique in integration. The chain rule has its own reverse rule in integration. Okay, let's do the first technique and see. Okay, let me go back here. I was saying this is the indefinite integral. When you integrate this, you write the integral, then you add the constant c all the time. You forget this, you are dead. Rest in peace. Lala ngokolo. I don't know if I said that right, but in my head it sounded right. So then the second one is the indefinite integral. No constant, you just evaluate your integral at these endpoints. That was the thing. Okay, but now in maths, guys, everything gets complicated. Same as integral. Guys, you go from integrating a simple thing as an x to go to integrating something like tan squared x over sec x. Something complicated, something that's going to give you a headache, something that can make you reconsider your future, something that can make you see an F7 knocking on your door. That's how maths can get. These techniques are helping us take these big, complicated integration problems. We are able to evaluate them without having to worry. Ne? Okay, let's come to the first one. The first one you did it in Materna. I think it was the last chapter in chapter 5, or the last thing you did, or they were just introducing you to it. It's called, okay, let me write one. I'm going to name them. So this one is called use substitution. It's called integration by substitution. Okay, when we say we substitute in soccer, you know what's the story? The people who watch soccer, let me admit this person. The people who watch soccer, ne, are Real Madrid fans. They are the only ones who matters in the world. Kazala guys. But the people who watch soccer, when you say substitution, another guy is coming in for another guy. Or we are taking another guy out and another guy is coming in. Okay. Now let's check. Um, this guy, I call him reverse of the chain rule, which is true. Reverse of chain rule. Ne? So here it's like we're gonna be reversing chain rule in a way. Now, the big question when it comes to the integration techniques is when do you use it? I get you can't just use it anywhere. How do I know that I need to use this type of, of integration technique? How do I know that this problem is suitable for use substitution? Okay, so now we have to answer when to use it question. Guys, I don't have a beautiful handwriting. In maths, they don't make a handwriting, guys. Ne? Okay. So, let me admit this person. Perfect. Okay. So, I don't like to write notes, but sometimes I just have to write something down so that you can see what is it that I'm actually talking about. So here, look for an integral where you can see, okay, where you can see a function and its derivative. Is derivative. Okay. For example, let me write a general term for you to be able to see exactly what is it that I'm talking about. Let me say the general term or the general form. Yeah? So it's the integral of, you have a composite function. Ne? Konje guys, what's the composite function? I can't hear you, or maybe it's my volume. Anybody else? I couldn't hear that. Guys, what's the composite function?
A function within a function.
A function which is?
Within a function.
Thank you. A function within another function. So let's assume you're finding an integral of a certain function f at x. So it's f at g at x. So you see, it's g at x inside f at x. That's a composite. Outside, you have a derivative of your g at x. Do you see what's going on? Outside, you have the derivative of the inside function. Because when now this is a composite, g at x is called the inside function. So remember, when you're deriving something like that, when you're using when you are on your derivatives, you were using a chain rule, meaning you were deriving the inside function, multiply by, then you derive the outside function. You remember that. So what does u substitution say? You need to set u to be equals to g at x, which is the inside function. Now, the very important question, how do you recognize an inside function? Usually, when you see brackets or when you see root, it can be cube root, it can be square root, it can be fourth root. Those are the operations that show us that this might be an inside function. But we're going to do problems now you can understand. So now, according to this general form, you take the inside function and you make it u. What do you do after? Guys, in integration, whenever you substitute, we're going to do something called trig substitution. When you substitute, you need to derive both sides. That's always the, guys, don't forget. You forget, you dead. Rest in peace. So now, after making you the inside function here, now you must derive both sides. When you derive this side, u, it becomes du. So it becomes 1 du, because this is just u. When you derive u in terms of, u in terms of u, it becomes 1 du, ne? Equals to, then this side becomes g prime x. This side you are deriving with respect to x, so it becomes g prime x dx, something like this. Then now you can continue. Okay, So now let's take a problem to see exactly what is it that we're actually doing. I think a problem is going to even make things easier for you and for you to understand. Okay, number one, we have an integral of x squared maybe divided by 1 minus x cube. Yeah, 1 minus x cube dx. Now, what's the first step here? You need to recognize your inside function. Okay, remember up here, guys, when this general form, it says you have an inside function here and outside you have its derivative. It looks like its derivative, even if it's not exactly its derivative, but as long as it looks like its derivative. What do I mean? Check this problem. You have 1 minus x cubed is inside this square root. I told you, whenever you see a root, think about, oh, here I might have my inside function. So when you take an inside function, don't just take one part, take the whole of it. Ne? You can say, oh, when you derive x cube, 1 x cube, you get 3x squared. Well, x squared looks like its derivative, if it's even though it's not its derivative exactly. Ne? So now what do we do? What's inside the under the square root? We take all of it and we make it u. Now this becomes our inside function. You take the whole of it. So here you can have y. Why am I saying y? Yo, I miss our y manji. You have u. It's equals to, at least I don't miss an x. If you don't get it, forget about it. 1 minus x cube. Konja, what's the next step, guys? You need to derive both sides. This is just u. So this just becomes du. It's equals to, this side becomes minus 3x squared dx. Are we fine, guys? Guys, everybody, are we fine?
Yes.
Oh, okay. So du is equals to minus 3x squared dx. So we need the dx in terms of du. Or we need everything in terms of u. That's the purpose of deriving both sides. So the dx, we can have it in terms of u. So now, I go back here, I substitute now. I say the integral of x squared, I leave it untouched. I don't touch it. I leave it as it is. I write it as x squared over, but remember, inside the square root, the whole thing became u, so I must put it as u. Now, I need to write dx in terms of du. Oh, I can just solve for dx here to make my life easier. So when I solve for dx there, it becomes du over minus 3x squared. So I can just come here, where there is dx, I put du over minus 3x squared. Okay, let's continue. So now, check. X squared and x squared are gonna cancel. So this guy and this guy will go. So what am I left with? I'm left with negative 1 over 3 here. I can just pull this guy out. So I can just bring negative 1 over 3 to the front. I'm allowed to do that. So here I'm gonna left it 1 over root of u du. Who's lost, guys, so far? Oh, so no one is lost. Ne? I can continue. You guys are smart people. That's why you're engineers. So negative 1 over 3. Now, when you derive or integrate, you might want to change this guy to a exponent, ne? Not and remove the root. So this guy becomes u to the exponent half du. So now we want to remove him from the denominator to the numerator. How do you do that? Remember, the sign of the exponent changes to negative. So this becomes u negative 1 over 2 du. So now you can integrate properly. Now, when I integrate this, it comes negative 1 over 3 still outside. Then inside, I'm going to have. Now, remember, I'm going to use the power rule of integration. I'm going to add 1 to the exponent. I'm going to add 1. Then whatever I get, I'm going to divide the whole thing with the same thing. So it's a reverse of deriving. Remember, deriving, you start by subtracting 1. No. You start by taking whatever is an exponent and multiplying the coefficient. If it's u to the exponent negative half. Now, when I derive, I start by taking this exponent negative half and multiplying the coefficient here. So it's gonna be negative 1 over 2 u negative 1 over 2. Then now I subtract. But with integration, you start by adding 1 first. Then you take this answer, which is negative 1 over 2 plus 1, you divide by the whole thing, right? So let's see how it's going to roll out for us. So when I say negative 1 over 2, when I add 1, how much do I get? I get negative 1 over 2. When I add 1, I get half because it becomes 1 minus half. This becomes half. So this half must divide the whole thing. So when it divides the whole thing, this just becomes 2. You know that, ne? Are we fine, guys? So this becomes 2. Now I need to add the constant because now I integrated. After integrating, immediately I need to add the constant. So now when I continue, the whole thing becomes -2/3 u to the exponent half plus c. I'm not done, guys. I'm not done. Why? Because my integral initially was in terms of x. I must bring my x back. It's equals to -2/3. But remember, what's my u? I need to go up there again. Here. It's 1 minus x cubed. So I must bring this guy here. 1 minus x cubed to the exponent half plus c. How is it, guys? How are you feeling? Is it fine? Can I
Yes.
bring another one? Oh, let me bring another one then. I love how we're moving. If everybody understands, then I'm happy. So let's say we have from 0 to pi over 4. Then I have sec squared x. Then I have sec. Okay, guys, the problems I do in class, I always do problems that I know that at the standard of your exam and your test. I think that's very important. And it's going to teach you also how to analyze such problems. I bring questions that are in the same standard as your exam and your test, because I know definitely those questions are going to help you understand how to approach the questions better. So let's say we have sec squared x multiplied by e to the exponent tan x dx. Yeah. Now, let's check. Which one qualifies to be our inside function? Guys, which one qualifies to be our inside function? Guys, you know what's a good thing about understanding your integral? In physics 1b, you will be integrating a lot. You'll be using these techniques of integration there, because to prove certain theories there, or certain laws like your Gauss law, you need to know your techniques of integration. So it's very important to pay attention. And also, if I solve a problem you don't understand somewhere, ask. So guys, I already told you with use substitution, you need to see which one qualifies to be an inside function. That's the one you're going to try to make you. So guys, here, which one qualifies to be our inside function? Ngibona ingozi. Oh, Ngosia. Guys, which one qualifies to be our inside function here?
Okay, can I try?
Guys, you passed MATEN.
Tan X qualifies to be our U.
Yes, tan X. What? Remember, guys, our general form. What was our general form saying, guys? I'm gonna go up here again to remind you. The inside function here, you check the one that is out looks like its derivative. Let's come back here. Now, which one is our composite function? It's e to the exponent tan x. Why? Because the function here is actually e to the exponent x, but now here it has tan x as an inside function. When you derive tan, you get sec squared x. Isn't it, guys? It still follows our general form. When you derive tan, you get sec squared. Or you guys don't know what's the derivative of tan? Matena, guys. You passed that. So such things you must be able to remember them. Okay, let me admit someone to the call. So guys, you must really be able to remember such things. Okay, let's continue, guys. No problem. Now, opposite function is tan. So I'm gonna let my u become tan x. Ne? So now I'm gonna derive both sides. So it becomes du is equals to. Sorry. So when you derive tan x, what do you get, Konje? A.
That's great.
I think AI must improve. Guys, if AI improves, we must be able to slap people through calls. They get all better mo ditlhogong. Pa, 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 pa. Why is the integral of tan x?
6 good things.
I just told you like 2 minutes ago. Sec squared x dx. Remember, I want the dx in terms of du. So I'm just going to say my dx is equals to du over sec squared x. So now I'm going to come here. Okay. 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 I might meet someone. Now, use substitution or any substitution when it comes to a definite integral, meaning the one with these boundaries. You must be careful. One mistake, you die. What does it mean? These limits are still in terms of x, so you must change them. You understand? You must change them. You have two options when you come to this step. Either you continue evaluating the, or you can evaluate the integral without the boundaries. After getting the integral, after, let's say your final answer is now cos x, when you substitute the u back. After, you must now bring back these boundaries now. Here, 0 pi over 4, and then evaluate your cos x at these boundaries as your integral. But now, what we can do, you and I, we can change the boundaries to in terms of u. Why? We do that so that at the end, we don't have to substitute the x's back. Or where there is u, we don't have to substitute tan back. Okay, let me show you what do I mean. Now I'm going to start with the lower boundary. When x is equal to 0, u is equal to tan. Where there is x, I put 0. What tan 0 is 0. Then I'm going to go to where x is equal to pi over 4. It's equal to u is equal to tan. Then where there is x, I put pi over 4. Tan pi over 4 is tan 45. The answer here is 1. So now I can substitute everything in terms of u, including the boundaries. So now I'm going to have 0 to 1. The boundaries even became way easy. Then 0 to 1. Okay, sec squared x, I just write it as it is. Sec squared x times e to exponent u, then times here, my dx in terms of du is du over sec squared x. Oh, this guy and this guy cancel. So I'm left with 0 to 1. E to exponent u du. It's equals to, guys, when you derive e to exponent x, the answer is just e to exponent x. Or when you integrate e to exponent x, the answer is just e to exponent x. This is e to exponent u. So the answer here is just e to exponent u. Then remember, I need to evaluate this from 0 to 1. I don't add a constant because it's a definite integral with boundaries. So this becomes, now I'm going to start at the upper boundary, e to exponent 1 minus e. I'm going to come to the lower boundary, e to exponent 0. So this becomes e minus 1. That's your answer for this question. Okay, let's do the last one, then you move to another type of integral. Ne? I mean, another integral technique. So let's do the last question. I think from a 2017 paper, they gave them something like ln x over x dx. Eish. Yeah, ne? Okay, let me rewrite this like this. I'm gonna say ln x times 1 over x dx. Eish. Okay, what are we making, you guys? It's like a function and its derivative. So when it's the function and its derivative, we make the function u. Can someone tell me what are we making u? So you can see what this looks like. This is f at x, then this is f prime x. When you derive ln x, you get 1 over x. Okay, let me admit someone. Yes, gift.
No, you took my answer. I was gonna say ln x. I think that's ln x.
Yeah. So yes, we make u ln x because that's f at x. It follows the same form, guys. This time it's just they're not composites, but it's the same form. Derivative function, you make function u. So that that's how things are gonna cancel. Please practice more problems so that you can master the skill. You can have the skill. So du is equal to, when you derive ln x, is what? 1 over x dx. So now I want to make my dx subject of the formula, so I can substitute it in terms of du. That's what you always do. So here I'm going to have dx is equal to x du. Do you see that? So now let's go and substitute. So my ln x is u. I leave 1 over x as it is. So here I have x du. X cancel x. My integral is u du. Guys. Now it's easy. Then this is u to the exponent 1. I add 1 first is 2, then I divide by 2. So it's 1 over 2 u squared plus c. Why is it plus c? It's an indefinite. It doesn't have boundaries. So I must add my constant all the time. You forget the constant, forget about the pass. 1 over 2, remember my u is ln, so it's ln. So it's, no, it's ln x. Why am I just writing ln? Patung. So it's just ln x. Remember, this guy is squared plus c. That's your answer. Okay, now you did u substitution, and hopefully you understand u substitution. It's fun, it's easy, it's straightforward. It's straightforward. Practice, practice, practice. Now find u substitution questions on the internet everywhere. Start practice, practice, practice. You are more than welcome to ask me questions, or even asking the group. You're more than welcome. So now the second technique, because now we go up, you understand? The second technique, we call it integration by parts. Ne? Integration by parts. Okay. Now I love to call this reverse of the product rule when you derive. Well, remember, u substitution, I said, it's kind of like the reverse of the chain rule. This one is kind of like the reverse of your product rule. Now, okay, every integration technique, it has its own standard form, general form, or its own general formula. Just like the previous ones, when we were doing your substitution, you saw how the standard formula is like, and you mastered it by now, and you know how to use it. It helps you to be able to use the technique successfully without having problems. So now, under integration by parts, okay, you can hear the word by parts, Oh, we're integrating by parts, which is true. But now, we use two variables, special variables. We use u and we use v. Okay, how do we use them? It says, if you have u dv, it's equals to, if you have something like this, an integration in this form, it's going to become u times v minus the integral of v du. Okay, what does it mean? You have a product of two functions. Whenever you have a product of two functions, how do you integrate them? Integration by parts is the best method for that. Remember, when you were deriving, when you had two products, products of two functions, when you derive, we're using what? The product rule. So that's why I'm saying this integration by parts, it kind of looks like the reverse of your product rule. So, okay, what does it mean? If we need to follow this general little formula for our integration by parts, for example, guys, let's say you have x times e to the exponent x dx. You can see, or this, you can name it f at x. You can see, or this, you can name it g at x. So now you have two functions multiplying each other. So when these two functions multiply each other, you can't use u substitution. What are you gonna make u? If you make ux, because that's the only thing that's gonna be valid. If you make ux, you're gonna have u times e to the exponent u. You haven't gone anywhere, you are playing. So now, since now it's strictly the product, there's no composite, so no u substitution that can work. In this particular case, you are forced to use your integration by parts. Now, what do you do? Let's check here and inside the integral sign. Okay, integral sign is here. I'm referring to the example I just wrote here. There is an integral sign here. There is an integral sign here. Oh, so meaning one of these variables must be u. One of these variables must be dv. Oh, or if I say u is equals to x, meaning dv must be equals to e to the exponent x. Now, be careful. Look at this. Whatever that you choose as u, you must derive it to get du. Whatever that you choose as dv, to move from dv to v, you must integrate. Oh, what does it mean? Let's check here. So here I have u equals to x. Or I'm going to say when I integrate both sides, remember, when I integrate u is going to be du, same as what I was doing with integration, with u substitution. So du is equals to, when I derive x, it becomes, what's the derivative of x? It becomes 1, but dx, remember, you derive dx all the time. So whatever I choose as dv, I must integrate both sides. Or when I integrate dv, it just becomes v. So now I must integrate e to the exponent x. It's just e to the exponent x, no dx. Please, when you integrate, no dx. You only get dx when you derive. When you derive, you get dx. Don't forget. So meaning now I have du, I have v, I have u, I have du. I can substitute to this formula. So now I'm going to go there. I'm going to say equals to, what's my u? My u is x here. Then I write x. What's my v? My v, I call it after integrating what I chose as dv. So multiply by e to the exponent x minus, what's my v, guys? My v is still e to the exponent x. What's my u? My u is my du. I'm looking for my du. It's 1 dx. Well, you see, du is equal to 1 dx. So here I'm gonna have dx. So now you can see, oh, this becomes x e to the exponent x minus, when you integrate e to the exponent x here, it just becomes e to the exponent x plus c. You are done. But now, hey, someone might be asking themselves, Sana, how do you know what to choose as u and what to choose as v? I also had that problem. One day I was chilling. Ne? I went online. When I went online, I actually find a very, very useful method to know what do you choose as u, what do you choose as du. I was like, wow. So the method was called, in capital letters, liate. Liate. Guys, don't say liate. Respect people. This is someone's mind. If I say sana is Seina, you must pronounce it as Seina. You say sana, I married you for life. So this guy liate, guys, I'm joking. I don't know if it's liate or liate because I was reading, but I'm pretty sure it's liate. So liate came with a very, very useful method of being able to choose your u and being able to choose your v. The method goes like this. So the focuses on u. Again, guys, don't forget what your formula looks like. It's u dv. It's equals to uv minus v du. So remember, you need to choose u and dv. dv being the one you integrate. Don't forget. So Liate says, when choosing u, look out for the following: log functions. So log functions, guys, is things like ln x. That's a natural log. Again, he said inverse trig functions. Inverse trig function, we're talking things like, example, arc sine x. That's an inverse trig function. And he said algebraic functions. I hope, guys, you are noting this down. Algebraic functions is things like x, maybe x squared, 3x. You know, those are algebraic functions. Also, he said look out for trig functions. So it's trig functions and their inverses. Is it? Yeah, trig functions and their inverses. Example, maybe can be a sine x, sine x, cos x. I don't need to write all of them. Lastly, he said look out for exponential functions. So exponential functions, it might be maybe e to the exponent x. Oh, Liate says look for log functions. When choosing u, what you can choose as a u. I get this product between two functions. Between those functions, one you must choose u, one you must choose dv. Ne? So he said when you choose u, look for log functions like ln x, a natural log ln, and look for inverse functions, or look for algebraic functions, use look for trig functions, or use for exponential functions. Fumanivo. Let's take an example and see. Let's say they're looking for integral of x squared e to the exponent 3x dx. We check. Oh, okay. Now this problem, it doesn't have I can't use u substitution because let's say okay, inside function is 3x, but when you derive 3x, you get 3. Because when you derive this, you must get something that almost like that. Maybe the difference is just instead of getting 4x squared, you're gonna get 9 over 2x squared. But you see, they kind of look alike. But when you derive 3x, you get x. So u substitution can work. You already see that. It cannot work. You need to use u substitution. So now we are going to follow Liate. Let's check Liate. Liate, the order, this order by Liate is very important. Check. Here we have x squared. Can someone tell me which category does x squared fall under on these type of functions I mentioned? Where does x squared fall under?
Algebraic function.
Algebraic, exact. Then where does e to the exponent 3x fall under?
Exponential function.
Aha. Which one comes first?
Algebraic.
Which one comes first?
Algebraic.
Algebraic. Aha. Since algebraic, according to my Liate, it comes first. I'm gonna say let u become x squared. Guys, no one is going to teach you this. I'm the only one in the universe. I'm the only one in the me and Liate, we are the only ones in the universe who gonna teach you this. So we have our u, meaning our dv is gonna be what? What's gonna be our dv? E to the exponent 3x. Now let's start with our u. Left hand side, you derive it. It's always gonna be du, guys, all the time. So this side becomes what? 2x dx. Now we come to dv. We need to integrate both sides. I need to integrate this side and I need to integrate this side. Now this becomes v is equals to, when you integrate e to the exponent 3x, what does the rule of e says? You're gonna derive the exponent and you divide by the derivative of the exponent. That's how you integrate e. So when I derive 3x, I get 3. So I'm gonna say the whole thing, I'm gonna divide by 3, which is just 1 over 3. Now, here, guys, it's an intermediate step. It's not the final integral. You don't need to write the plus c constant. Someone might be asking themselves, why are we not writing the plus c? No, there is no need to write the plus c. This is not the final integral. No need to write the plus c. Now, remember the formula. It's u dv is equals to uv minus integral of v du, right? That's the formula. So now let's plug in the formula. So it's the integral of x squared. What's my dv? My dv was e to the exponent 3x dx is equals to, what's my u, guys? X squared times what's my v? It's 1 over 3 e to the exponent 3x, right? Minus integral of v du. What's my v? You substitute 1 over 3 e to the exponent 3x. What's my du? My du is 2x dx. So multiply by 2x dx equals to. Now I need to just deal with this side to find the integral. Everybody, are we together? We are not leaving any part. Now, guys, what's left here is just to multiply. So, guys, let's multiply. So here I have x squared over 3, x squared over 3, yes, e to the exponent 3x minus, here you can see I have 2, I can say 2 over 3 and take it out. So minus 2 over 3, so in the brackets, in the integral, I'm gonna left it e to the exponent 3x times x dx. Now, you only need to worry about this integral. Ne? Can someone tell me how are we going to evaluate that? Okay, let me just do this. Let me say this becomes x squared e to the exponent 3x, all of this over 3 minus 2 over 3 e to the exponent 3x times x dx. Now you check. I still have a product of two functions, e to the exponent 3x and x. If I use substitution, is it gonna work? No, because when I check my inside function 3x, when I derive it, I just get 3, and this is x. The derivative of 3x doesn't have an x. I need to use integration by parts again. Now you do this. You take this part You evaluate it one side. Or you're gonna take x to the exponent e to the exponent 3x dx. You're gonna evaluate it at the side. That's how the test be. Some people, when they get here, they're like, ish, it's impossible. Like I said, these problems are from your semester test and your exams. I just don't take random problems. Now, this problem needs another integration by part. So integration by parts, guys, you can do it 2 times. Just know that. So this time we check. What do I make you guys?
Which one comes first? Algebraic. You see?
Aha. Then what do I make you? X, isn't it?
Yes.
X falls under algebraic. So U is equals to so guys, you must don't forget or algebraic. How do they look like? Where are they? Don't forget or algebraic. How do they look like? And trig. How do they look like? You know trig functions. How? I'm pretty sure everyone knows trig functions. So now I'm deriving this side. Du is just gonna be equals to 1 dx, which is just dx. It's just u equals to x. So remember, now I need to choose my dv to be e to the exponent 3x. Then my v, we already evaluated that, right? Then my v becomes 1 over 3e to the exponent 3x. So now x e to the exponent 3x dx becomes uv. Yeah, remember the formula. What's my u? X. What's my v? 1 over 3e to the exponent 3x minus, what's my v? V du. Don't forget, 1 over 3e to the exponent 3x. Now, what's my du is just dx. Now we continue. Now we can continue what we're doing. So this is x over 3e to the exponent 3x minus, I can pull out 1 over 3 in the brackets, I'm left it. Why do I keep saying brackets? I see danger. Now I'm left with this. So I can say this is x e to the exponent 3x over 3 minus 1 over 3. Guys, what's the integral of this? This one I beat all of you guys. I'm sorry. Guys, what's the integral of e to the exponent 3x?
One over 3e to the power 3x.
It's 1 over 3e to the power 3x plus c. So this becomes x e to the exponent 3x. Oh, manch, I'm cancelling instead of dividing. What's wrong with me? Over 3 minus 1 over 9 e to the exponent 3x plus c. Hish! Now, guys, remember, this was just part of the solution. But remember, this guy, I was evaluating this guy on the main problem. I need to substitute all of this back here so I can find the integral that I was actually looking for. So what on now? The final integral is gonna be the final integral will be, so now I need to copy the whole thing here, which was x cubed e to the exponent 3x over 3 x cubed, I think it's x squared e to the exponent 3x over 3. Then let me go check. Minus 2 over 3. So it's minus 2 over 3. Then into the whole thing. X e to the exponent 3x over 3 minus 1 over 9 e to the exponent 3x. All of this plus c. So guys, what's left here is just to multiply the brackets at the like terms, and that's it. What's important is, did you get the concept, guys? Do you see how to use integration by parts? Can you use it twice? Okay. Exam, I think it's 2022 or 2021. They did this. Lot of police dropped. They just did this. They were just like, please find us an integral of arctan x dx. They just said this, guys. Nothing more. They just said this and that's it. They just said, find the integral of arctan x. What do you do in this situation? Guys, whenever they ask you to find an antiderivative of an inverse function, you use by parts. Someone, I know you have questions. Mara, we only have one function. What's the other function? I only see arctan x. You said by parts we must have two functions multiplying each other. Now, the other function is 1. The other function is 1. Ne? 1. Now, let's go back here. Where are we? Let's go back here. 1. Where does it fall under? Inverse, log functions, algebraic. Where can 1 fall under, Mar?
Algebraic.
Algebraic. So you have an algebraic and inverse. Which one comes first?
Inverse.
So what's gonna be our U?
Arctan.
So U is gonna be arctan x. Now we're gonna derive both sides. Du is equals to, what's the derivative of arctan, the inverse of tan? It's 1 over 1 plus x squared. Thank you so much. Dx, right? So now my dv is equals to 1. I need. So now when I remember my dv, I need to integrate to get the v. So guys, what's my v in this case?
X.
X. So now I'm just gonna write the formula. Remember, formula you can write it at the corner there when you write, so you don't forget. It's uv minus v du. Don't forget that. So now what's our u? Arctan x. Arctan x times. And then what's our v? X minus. So vx. Then what's my du? My du is 1 over 1 plus x squared dx. Okay. So now let me scroll up. Let me scroll up. Equals to arctan x times x. It's equals to no. Okay, x here it's minus. Then I can just put the x at the top there. It becomes 1 plus x squared dx. Or someone can see. How are we going to evaluate that integral, guys?
Use substitution.
Thank you. Sorry, I'm happy. Thank you. You can see at the bottom you have 1 plus x squared. It looks like when you derive it, you get x. So it looks like when you derive it, you get x, which is at the top. Ne? So you can see. But Mina, guys, since I've been integrating, I can already see that this is a lean problem. Why do I think it's a lean? Whenever you have a derivative at the top, ne, and a function at the bottom, dx, whenever you have something of this nature, you have a function at the bottom, you have its derivative at the top. The answer to this is just lean, absolute value of the function itself. Okay, let's take an example. Let's say you have sine x here over cos x. When you derive cos, you get sine. Okay, you get negative sine. I don't want it to be like that. Because I want to. Let's say you have sine x here, then you have cos x at the top. Ne? Dx. The integral of this, you don't sweat. You check. When you derive sine, you get cos, which is at the top. Oh, the answer is just lean, the function itself, which is absolute value of sine x plus c. Do you see that? But where did I get this rule? You get it from U substitution. So even if you don't master this rule, you just use U substitution all the way. You'll never go wrong. The answer will be correct. I can already see here answer is gonna be 1 over 2. Because when you derive 1 plus x squared, you get 2x, but at the top is just x. So to counter that 2, I must multiply by half. Okay, maybe you are not there yet, but don't worry, you are coming. So x arctan x minus. When I use U substitution there, what is it that I'm gonna make you? Someone just came now. Let me admit them. What is it that you're gonna make you guys?
1 plus x squared.
Thank you. So you're gonna make U to be 1 plus x squared. Remember how do you deal with the U substitution? Now you gotta derive both sides. So this becomes du, it's equals to 2x dx. Ne? So now I want to, people are just coming in now. I apologize. Okay, now we can continue. So now I need to find dx in terms of du so I can put it there. Ne? So I'm gonna have dx is equals to du over 2x. Ne? So now I'm gonna come here. X, I'm gonna leave it as it is. Over 1. Oh, I forgot to this guy, I made him u. I forgot to I made this guy u. Ne? Okay, I was admitting someone. Let's continue. So remember, I have my dx in terms of du, so I can just put du over 2x here. This guy cancels this guy. So what do I have? I still have x arc tan x minus. So now I have what? 1 over u du. 1 over u du, it's ln u. Because when you derive ln u, you get 1 over u, right? So I'm going to have x. Oh, I have 1 over 2 outside, ne? Because here, remember, I'm left it over 2. So I can just pull the half out. That's what you always do, so that your things becomes easier. Then the constant just multiply later. So here I have arc. Okay, I forget the arc here. Tan x minus 1 over 2 ln u plus c. Now it becomes x arc tan x minus half. So I need to substitute the u back. So guys, this one must always be positive. Ne? The input inside the ln must always be positive. But this is 1 plus x squared, guys. X squared will always be positive. 1 will always be positive. So there is no need for me to put absolute values. So I can just put it. So this one I'm allowed to just say ln 1 plus x squared, because it will never be negative, guys. It will always be positive. That's the oh, I forgot plus c. Yay, yay, yay. This is an indefinite integral. You must always add plus c. You forget plus c. Remember what I said, guys. You are dead. Let's do the last problem answer by parts. Then after we do the last technique for the day. Ne? So I'm gonna do the last problem under integration by parts. So let me say e to the exponent x cos x dx. So I'm gonna, now we check. We see we have a trig function and we also have an exponential function. Konje, what's my rule? My guy up there told you exactly what to do, what to make you. But both of these, they're in his list, in his hit list. Konje, what do you check? You check the order. Now we are going to check, guys. E to the exponent x, what type of a function is this?
Exponential.
Exponential. Then cos x, what type of a function is this?
Trig.
It's a trig function. Ne? Are you ready to go to my boy Liat? Let's go up there. Now we are on Liat. Now we check. Who comes first? We have trig, we have exponential. Who comes first?
Trig.
Trig, ne? Perfect. Now we go back. Long distance travel. I'm sure my 480 taxi. Okay. Now, what came first? Is it trig or exponential?
Trig.
So what do we make u?
Cos x.
Cos. Thank you. So u becomes cos x. So meaning my dv is going to become e to the exponent x. Now we are sorted. Now we can continue working. So here, du is equals to, when I derive cos, I get negative sine x dx. Ne? So here, v is going to become e to the exponent x. It doesn't change. Now, this problem is very interesting, guys. This problem is very interesting. You're going to see right now why is the problem interesting. Now, we continue. We're going to say e to the exponent x cos x dx. It's equals to, now I substitute, guys, my u, v, and du. So what's my u? It's cos x. Cos x. What's my v? E to the exponent x minus into integral now. So what's my v? It's e to the exponent x. What's my du? I'm substituting. Remember the formula. Don't forget it. It's minus sine x dx. Right? Perfect. Now let's continue. This becomes e to the exponent x cos x minus minus. So minus minus, I can say here it's plus. Ne? It's gonna be plus integral of e to the exponent x sine x dx. What do you see? Can someone tell me what do they see?
We're gonna use
What
integration by part again.
again? Exactly. So now we need to evaluate e to the exponent x sine x dx. When you visit our guy Liate, this is still an exponential and a trig. So we still start with a trig. So we make u is equals to sine x, then du, when you integrate sine, you get cos x dx. So when you make dx our subject of the formula, it becomes dx is equals to du over cos x, right? No. Yeah, actually it's fine. Yes. So now my dv becomes e to the exponent x, meaning my v becomes e to the exponent x. Perfect. So now I can substitute on my uv dv thing. So it's equals to, now my u becomes sine x, my v becomes e to the exponent x minus the integral of, what's my v, e to the exponent x, what's my du, it's cos x dx. Okay, let's substitute back here. Let me rewrite. The original one was, remember guys, our original was the integral of e to the exponent x cos x dx. It's equals to, ne? That's our original. That's what you wanted. So I'm gonna write this part, and this part we evaluated it down here. So this is equals to e to the exponent x cos x minus. So now minus, remember now I'm on this part. That's the part I was evaluating just now. And the answer is here. So I'm just going to substitute here. So when I minus, this is just going to be e to the exponent x sine x. And then this becomes, wait, I'm checking if I'm this is the part becomes minus e, what's the way, minus, this becomes minus, this becomes plus. Yes, I'm substituting here this part. So yes, then this becomes minus integral of e to the exponent x cos x dx. Guys, are we together so far? Did you see the substitution here? When I was substituting that little part, I was integrating by parts again. I'm just taking it back now. Did you see it so far, guys? Are we all together?
Yes.
Okay. Check something. We have this guy both sides. We have the integral of e to the exponent x cos x dx this side. We have e to the exponent x cos x dx both sides. Hey, Hannah. And that's the guy I'm looking for. I'm gonna let I become that guy, e to the exponent x cos x dx. I'm gonna let this guy becomes I. If this guy becomes I can transpose. When this guy here comes now to join this guy here, it becomes 2i that side. Then in this side, I'm left with e to the exponent x cos x plus e to the exponent x sine x plus c. Are you aware, guys? No. I can't write plus C before it's the final answer. Are you aware, guys? So far, did you see what happened?
Yes.
Or you saw what happened? Everybody, you saw what happened, ne? Because guys, you meet such cases most of the times. The integral you're looking for, now it appears in the answer. So meaning now you must transpose it. Do you see where integration by parts can trick you? So now I'm gonna solve for I. I is the one I'm looking for. Then becomes half e to the exponent x cos x plus half e to the exponent x sine x plus c. Now this is the answer. Now this is the answer you're looking for. Everybody, are we fine? Can we do the last integration technique? Do you still have energy for one more, guys? Please
Yes.
talk. I love the energy. Okay, then let's do the last one. So the last one. Okay, guys, can I get a feedback on the first two? Did you understand? Because that's very important for me. Do you understand, guys, the first two?
Yes, sir.
Please unmute and confirm that yes, you understood the first two techniques.
Yes.
And after this question, please go do problems. Don't just relax, guys. Like I said at the beginning of the session, it's very, very, very important that you practice your work. So after this, now go find problems now online. Find worksheets and work on them. Okay, the last technique for the day is integration by something called partial fractions. So now let's say in the test, you see all the first two methods, they're definitely not gonna work. They won't work. By parts won't work. Use substitution won't work. Now you go to this one. Let me write the number 3 down. Now this one is integration by partial by partial by partial fractions. Oh, okay. I love to call this inverse of ratio. Is it the ratio rule? Let me just call it ratio. Nah, actually, let me call it with its official name. Someone is confused. Quotient rule. Because can someone remind me where are we using a quotient rule? Someone just invite me. Konje, what type of a function or functions were they forcing us to use to derive them using the quotient rule? Actually, where were we using the quotient rule, guys? In Matena. Where like what happens for us to use the quotient rule?
Body fraction. Is that not where you use it?
Who's answering? Who's answering?
No comment.
Hey, wait, let me check. Guys, where do we use the quotient rule? Yeah, we got a fraction. But can someone like make it more clear? True, got a fraction. That's right. Where do we use the quotient rule, guys?
And a function is dividing another function.
Thank you. We use it when two functions are dividing each other, specifically polynomials, to be specific for this one. So, so now integration by partial fractions is gonna work. Is the method we use for rational functions. What do we mean rational functions? When maybe there is a function p at x dividing a function q at x, where p at x and q at x are polynomials. Guys, they must be polynomials. You know what polynomials are? X cubed minus 3x. X to the exponent 4 minus 2x cubed plus 2x squared plus 3. Those are polynomials. That's what I'm talking about. So we're going to have polynomials. We have the first polynomial being p to p at x divided by q at x. These are two polynomials dividing each other. Now that's when we use, now we need to use integration by partial fractions. But there are rules. You don't just jump and start doing things around. Rules. Let me call them steps. Let me say steps. Yeah? The steps. Number 1, check the degree. Guys, degree, I'm not talking about degree Celsius. Someone is checking weather. No. Check the degree. Listen to me under the degree. You don't listen to me, you'll die. I'm gonna write these down so you understand, because I feel like a lot of people you don't understand why they gave you 0 out of 6 in a semester test, and you are busy querying. And what's even in maths, guys, the maths department, when you query, they remark the whole script, and it turns out they gave you 7 marks by mistake. They take it back. That's how they work. You lodge a query, they remark the whole script. So now you listen. Okay, remember my polynomial here. I'm gonna reference with p at x being a numerator, then q at x being my denominator. Ne? So now let me write. If the where am I? Okay. If the numerator, ne? If the numerator, my numerator being p at x is greater. I'm talking about the degree, by the way. The degree. Guys, who can tell me what am I talking about when I say the degree? Guys, I'm talking about the degree of an exponent. The degree of their exponents, those polynomials. That's what I'm talking about when I say the degree. But you're gonna see with the examples. So if the degree, I guys, writing is gonna take the whole day. I. So I'm just gonna use sample. Check the degree. If the degree of p at x is greater or equals to the degree of q at x, I have bad news for you. This method won't work. For example, if you have something like this, x to the exponent 4 minus x cubed plus 2x over x squared minus 2x plus 4. Now check, guys. Can you see that the degree of exponent of the numerator is greater than the highest degree of exponent of the denominator? Do you see that? Yes, please confirm. Do you see that? That's what I literally wrote there. I just want you to see how does it look like. The highest exponent in the numerator is x to the exponent 4. The highest exponent in the denominator is x squared. Do you see that, guys?
Yes.
Now, if it is like this, I have bad news for you. You cannot use partial fractions. Before you use it, you must do what you call, you must perform something we call, I don't like it at all, long division. Long division. All right, guys, you see now, ish. Yeah, you must know long division all of a sudden. You see, so now if it happens that the degree of your numerator is greater than the degree of your denominator, you cannot use partial fractions. You must first perform long division. After performing long division, then now you can use your partial fractions. Okay, what do you do? Number 2, factorize denominator. Factorize denominator, guys. So remember how to factorize. You remember how to factorize from grade 11, 10. They taught you how to factorize for the first time in grade 9. So guys, I want like really show you when you factorize, you make pair of brackets, then you check the sign of the last term, then you check the sign of the middle term. You know how to do that, I assume. Or there is anybody who doesn't know how to factorize? Then the third step, we call it decomposition phase. Decomposition. Now, listen here. For each factor, for example, when you have ax squared plus bx plus c, you're going to factorize these maybe to factors ax plus b and ax plus b. I just assume. Maybe these are your factors when you factorize. For each factor, when you decompose, you get the term a over ax plus b. Triangle nyakamo. Le passed you maths, guys. You passed your math in high school. You are no longer doing Euclidean geometry. Maybe the triangles miss you. Angles at the center, they are twice the angles at the what. So this is A, this is plus B. So for each factor, so this is the first factor right in the first bracket. You're gonna get this term plus. When you move to the next one, it's gonna be B, no longer A. You need to, this variable here has to be B over. Okay, they can't be the same. There is a special case. Let's say C. It's gonna be plus B over, now it becomes AX plus C. Okay, so let's look at the second scenario. Let's say it's repeated AX plus B squared maybe. When it's repeated, how do you write this? You write this like this. It's gonna be A over AX plus B, right? Plus, then it's gonna be B over. This time, you don't write AX plus B solo. you square it because here it's squared. So if it's 3, if it's to the exponent 3 here, it's gonna be ax plus b squared, then ax plus b to the exponent 3 until you reach the degree of exponent here. So this one is gonna be ax plus b all squared. Whoosh. Yeah, ne? So for a quadratic equation that you can't do anything about it, let's say it's 3x squared plus 2x plus 3. You can't do anything. You can't factorize this. You can't do anything. When you reduce it, you decompose it, it's just going to be ax plus b. So it's two variables, one of them multiplied by x divided by ax squared plus bx plus c. Eish. Okay. Let's do, okay. In this case, it's going to be 3x squared plus 2x plus, is it plus 3 there? Yeah, it's gonna be like this. I think the better way of doing this is by solving problems. So guys, the aim of this, we need to solve the coefficients a, b. You see these capital letters here, these coefficients. Now we need to be able to solve them. But to boost your understanding better, let's take a problem so you can see exactly what is it that I'm talking about. Okay, let's take a problem, guys. So the first problem is 5x minus 3 divided by x squared minus 2x minus 3 dx. You check. What's the first step? You check the degree. You guys are going to confirm with me. Are the degrees correct? The degree of the numerator must be less than the degree of exponent, the highest degree of exponent of the denominator. Is that the case, guys? Does it pass?
Yes.
Oh, now what's the next step? Okay, we check the degree, right? What's the next step? We need to factorize. You need to factorize the denominator. That's the first step that I wrote up there. So forget about the integral sign and deal with the partial fraction. Forget about it for now. So I'm gonna write 5x minus 3 over. Now I need to factorize the denominator as that's the second step. So when I factorize it, it becomes x. What the factors 3 and 1 minus 3. Signs are not the same. The middle term is negative. The bigger term is going to take the negative. So it becomes x plus 1, right? Equals 2. Now we are going to decompose it. Remember, the first term, x minus 3, this, x minus 3, is going to decompose into a over x minus 3 plus. The second one is x plus 1. It's going to decompose as b over x plus 1. Guys, now do we know how to decompose? Please confirm. For this problem, did we see how we decompose? The 2x, the 5x
Yes.
minus 3 at the top. The 5x minus 3 at the top. No. Don't worry about that. Decompose looking at the denominators, factorized. So are we fine with decomposing for now?
Yes.
Yes.
So what's the next step? The next step is we need to multiply everything by x minus 3x plus 1. All these, whatever you just decomposed, we're going to multiply everything by it. So when you multiply this by x minus 3x plus 1, I'm only left with 5x minus 3. Here, x minus 3 will cancel. I'm going to be left with a into x plus 1 plus b. Here, x plus 1 will cancel. I'm going to be left with x minus 3. 3. Yeah, 3. Okay. So far, so good. Now we check. We need to solve for A and B. This is the strategy when you have a problem of this nature. You check. You need the number to substitute as an x there where there is A, so it can make the whole thing 0. What's that number? -1. Check. If I let x become -1, I'm going to have this side 5 into -1 minus 3 equals to a into, here I'm going to have 0. -1 plus 1 is 0. So I'm going to have b into -4. You see, a goes. Then here I'm going to have -5 minus 8. -8 is equals to b into -4. Therefore, my b becomes 2. Guys, your answers must be 1, 2, 3. If your answer is like 33 over 44, you are wrong. So now we come to we come to B. So here you're gonna say let x equals to -1. Now we need to solve for B. We solve for B and we need to solve for A. What is it that you can make x that will cancel the B so we can solve for A?
3.
3. So I'm gonna say let x be equals to 3. So it's gonna be 5 into 3 minus 3 equals to A into 3 plus 1 is 4. It's equals to, this becomes 0. 3 minus 3 is 0. That was the aim. 5 times 3 it's 15. 15 minus 3 it's 5 times 3 is 15. Yes, it's 15. Then 15 12. This becomes 12, I think. So this becomes A into 4. Then my A becomes 3. Now we are done. So now the whole thing decomposed becomes A is what? A is 3 over, let's check. We need to substitute here. A becomes 3 this becomes 3 over x minus 3. Now we substitute it here. 3x minus 3 plus, this becomes 4 over x plus 1. Now the new integral that you can evaluate is 3 over x minus 3 plus 4 over x plus 1. Since it's two terms, we must put our brackets around the integral side, or you can distribute the integral. You are allowed to do so. Meaning this integral, we can write it this way. I'm out of pages. So meaning this integral, you can write it like integral of 3 over x minus 3 dx plus integral of 4 over x plus 1 dx. You can do that. Ne? Okay, let me erase here because you already saw. I'm going to add pages for the next problem. So for now, I want to erase here because you already saw what's going on here. I already decomposed. So for you to not use, you can use substitution here for this to evaluate both 3 over x minus 3 or 4 over x plus 1. You can use substitution, but this is what I'm gonna do. It's equals to, I take 3 out on the first one, I'm left with 1 over x minus 3 dx plus, I take 4 out on the first one, I'm left with 1 over x plus 1 dx. Guys, whenever you see 1 over x, the highest degree is 1 at the denominator, the answer is just lean. Now we go back to the rule I just told you guys, or whenever you have a function at the bottom, when you derive it, you get what's at the top, it's a lean. When you derive x minus 3, you get 1, because negative 3 becomes 0, x becomes 1. So to make your life easier, just know whenever you have 1 over or a constant over, the denominator where the highest degree is just 1 is just lean to save your time. So it's lean. Mari must take out the constants first, so you are left with 1, so that you don't get confused. Remember, lean must always have the absolute value x minus 3 plus. Here becomes 4 lean, the absolute value x plus 1 plus c. And now we find, guys, did we see what's going on?
Yes.
It's only one person who has been confirming the whole session. Others, I want to do another problem. Ne? Others, do you understand, guys?
Yes, sir.
I want to do one more problem. If I do one more problem, then I'll be happy. Okay, so my problem is like this. Ne? The integral of 2x squared minus x plus 4, all of this divided by x to the exponent, x squared plus 4x dx. What's the first? No. It can't be x squared. They can't be equal. Remember, if they are equal, or the numerator has a higher degree of exponent than the denominator, it comes you to long division. Man, why am I canceling that? So at the bottom here, I must have x cubed. Okay, now it's fine. So who can tell me what's the next method? Guys, what's the next method? Can someone tell me what's the next method?
Factorize the denominator.
Factorize the denominator. So meaning now I need to, or it means here I need to factorize. So here I can only factorize by taking out the common factor. So I have x over x squared plus 4. Okay. Now the first term is x. It's just a. It's a linear. It's just a over x plus x squared plus 4. It's a quadratic. So quadratic must be in the 4. Since I already used a here, what I'm going to start with b multiplied by x plus another constant c divided by that quadratic x squared plus 4. So do you guys now see is the things that I wrote up here when I was introducing the topic on how to decompose them? Is everybody fine? So now what do? The usual. We solve. Or you start by multiplying by the denominator first. Or here I'm gonna be left with 2x squared minus x plus 4 equals to x cancel x here. So I'm left with x squared plus 4 plus here I'm left with bx plus c. Now x squared plus 4, it's cancelled. Then I'm left with x2. Okay. Now let's check. This one, if we try to use the method we used back then, we're not really going to be successful. The method of eliminating is not really going to work out. Why? The problem is the x squared where there is a. What are you going to substitute there to make that thing 0? Nothing. Do you see that, guys? So what do you do right now? We use what they call the coefficient method. This is what you do. This side you have 2x squared minus x plus 4. What you do, you multiply the brackets first. Ax squared plus 4a plus bx squared plus cx. So this is what you do. You're gonna equate the coefficients of x squared. You're gonna equate the coefficients of x. So now we're gonna start with the coefficients of x squared. So this one, so I have 2 this side, it's equals to that side I have a plus b. Do you see that, guys? Guys, do you see that? Please confirm, guys. I know you're tired, guys. It's the last problem. It's okay. Just wake up for the last 5 minutes. Did you see that? Did you see? I equated the coefficients of x squared because I cannot eliminate the last method I used. So do you see this? Guys, please confirm.
Oh, yes, yes, yes.
Now I'm going to equate the coefficients of x alone. This side I have negative x, so the coefficient is just -1. You don't put the x, it's just the coefficient. That side, what's the coefficient of x that side, guys?
C.
C.
C. So automatically it tells me what C is. So now I'm going to equate the constant, the one without excess. Wow, without excess, that must be a good life. So that side, the coefficient I have 4, it's equals to, is it 4? Yes, it's 4. That side I have 4a. Do you see that? Then my a becomes 1. Then I can already see where my b is also 1. So everything is 1. Do you see that? So I'm going to come to the decomposition now and substitute. So I'm going to have my integral of 1 over x plus 1x plus 1. So I can just say x plus 1 over x squared plus, let me go back, the x squared plus 4. So this is x squared. Is it x plus 1 or x minus 1? Hey, Umuntu is getting old now. Oh yeah, it's plus 1. It's plus 1, right? No, man, C is -1. Yo, C here, guys, -1. Sorry. So C here, it's supposed to be -1. C -1. Then here at the bottom, is it x squared? Yeah, it's plus 4 here. So I'm gonna close it or distribute it if I like, dx. So now we're going to integrate. I can just distribute the integral, right? So when I distribute the integral, I'm going to have 1 over x dx plus x minus 1 over x squared plus 4 dx. This guy, I can break him. The fact that at the top there is x minus 1 over the whole thing, I can just break this up. I can change this into x over x squared plus 4 minus 1 over x squared plus 4. That's just maths. I know. What's the integral of 1 over x, guys?
Then
I want
X.
to. Is what?
Sleep.
Yeah. Ugh. This triangle keeps coming. So this is lean absolute value of x plus. So this guy x over. Guys, if you learn everything that I do in these sessions, you are ready for test. Dx like this. I broke it and even separated the integral in the same time. So now let's check the middle one. The middle one. How are you going to evaluate the integral?
Use
Use substitution.
Yes, use substitution. So you're gonna make u to be x squared plus 4. Then it's gonna be du is equal to 2x dx. So you can see our dx is gonna be du over 2x, right? So you can see or this is gonna be integral of x over u times du over 2x. X cancels x, then 1 over 2, I can take it outside, it's 1 over u du. So 1 over 2, 1 over u, it's ln u plus c. So 1 over 2 ln, what's my u? X squared plus 4. So I already know what the integral is gonna be, 1 over 2 ln x squared plus 4. But the shorter way, what I do is the lean rule that I just told you about. I know I have integral of over x squared plus 4. I know if the derivative is at the top, it's just lean. But at the top, when you derive x squared plus 4, you get 2x, right? But here it's just x. So I counteract my change with a half. Do you see that? This is still the same thing, guys. These two are still the same thing. But I want to apply my lean rule of having the function at the bottom at the denominator. When you derive it, you get the one at the top. The answer is just the lean of the function. Do you remember that, guys? Are we together?
Yes.
But when I derive the bottom part is x squared plus 4, I don't have it. I don't have 2x at the top. So what I do, I add 2 and I immediately multiply by half. It counteracts the change. The value doesn't change. So now my answer is just 1 over 2 ln the function x squared plus 4. Do you see that? Okay. So now let me write down the answer. So this becomes ln x plus this becomes 1 over 2 ln absolute value. This one, there's no need for absolute value because x squared will always be positive minus. Aha. So now let's check. This integral, it's in the form of 1 over x squared plus a squared. What do we say? We're saying if you have such a problem, the integral of this is 1 over a arc tan x over a, right? This is what the integral is. Now let's check here. What's our a in this case?
2.
2. So it's 1 over 2 arc tan x over 2. Let me erase this to write my plus c. So if it's an indefinite integral without boundaries, don't forget your plus c. Plus c. That's the answer. Yeah. What a ride. We've been here. How do you feel? How do you feel after your first class, guys? Hey, do you have hope?
A bit of hope.
But do you understand some things?
Yeah.
Yes.
Because the idea is for you to get some things like you don't have to perfect it now. Guys, before the semester test, You'll be dangerous with integral. Don't worry. Don't worry. I know, guys, for the first time, I don't expect you to master everything. But things like Liate, I expect you to have noted them down. And next time when you meet, you know them. You understand? But so yeah, I was just giving you the foundation. And with this foundation, I want you now go do some problems and ask me questions. You understand? Ask me questions. You know where to find me. Text me and ask. How do you approach this one? I'll refer back to this class. Do you remember in class we said, you understand? Go to your partial fractions. Use substitution is the easiest, and do your integration by parts. Practice, 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 practice. Unless if you want me to give you recommended problems, you can reach out and I'll give you from the textbook. And I believe from 2 sessions, you'll be ready for any integral that will come in the exam and a test, semester test. Semester test 1, guys, 100%, no excuses. So from me, yeah, it's been a long session, guys, because you guys are my third class of the day. So yeah, but I enjoyed this class more. I love this maths. Maybe it's because I love engineering in general. So how was the session, guys?
Productive.
Nah. Oh, I want to hear from a guy. How was the session?